Okay, so it's high time to start our workshop. So hello everyone, welcome to the first day of our quantum computing workshop QBronze166. My name is Pavel, I'm one of the organizers. Uh, I'm the chairperson of the board of QWORD, which is an international organization that developed the educational materials, bronze, um, on which we base our workshop. I'm also the founder and CEO of Quantum AI Foundation, which is a non-profit organization supporting the development of new technologies, the education, research on new technologies, and collaboration, especially on quantum computing and AI. At the beginning, I will tell you a few words about our workshop. Then I will tell about QWORD, QPoland, and Quantum AI Foundation, as they are the organizers, formal organizers of this workshop. And then I will uh, give the floor and the Zoom to Mateusz, our instructor, who will lead the sessions for the next days. Yes, so as you can see, we are starting now, but we'll have 5 days of classes. Today, tomorrow, on Friday, and then Monday and Tuesday. Each day will start at 6 p.m. UTC plus 2, so it's time in local time here in Poland. The instructor is Mateusz Anuszewski. I can see that Mateusz is already with us, which is great. Thanks for joining, Mateusz. We also have several mentors. They're also available on Discord. Beside Mateusz, there's only Józef Kasprzycki, Adam Wesołowski, Michał Szaniewski, Konrad Łącki, Michał Malik, and I. So I will try to answer the questions related to organization and all the matters about organization, maybe also some merit questions as well. We'll see. The other mentors will try to support you when we have difficulties with installing the environment or you have some questions about the lectures. All the nice graphics that we use were prepared by Aga Wolska, so she's also a member of our team. As I said, this workshop will be based on the bronze materials developed by QWORD. All the lectures will be on Zoom as today. The link will be the same. Uh, Discord is our backup option, so I hope that all of you have joined our Discord server. We have a dedicated Discord server with several channels. So if there are some technical issues with Zoom, we can always try to move to Discord. But by default, the lectures will be here on Zoom. But if you have any questions, of course, you can try to ask your questions here on the chat. But the default way of asking questions is just by posting your questions on the dedicated Discord channels. So when you open our Discord server, you will see that there is a special category that's named Help, and there are some dedicated channels where you can ask questions about the installation, about the math, physics, Python, Qiskit, homeworks, and so on. So about the homeworks, you can receive a certificate after solving the homeworks. There will be 5 quizzes, and you must get at least 50% of points from each of these 5 quizzes, and at least 70% in total. And I will soon send you invitations from Canvas. So Canvas is a platform in which we uh, just organize all these quizzes. Um, and there will be the final deadline for completing the last quiz is October 20th. But as far as I remember, the deadline for the first quiz is October 16th. So it's about 2 weeks from now. And then, as I said, there will be 5 homeworks. So the deadline for the first one, for the first quiz, is October 16, then October 17, 18, 19, and 20. So that's the plan. Do you have any questions regarding the organization in general? As you can see, we are recording the session, so hopefully the video will be later available on our YouTube channel, and we'll try to share the link by tomorrow. I do not see questions now. Let me just check the chat. I do not see the questions there either. So, okay. So I also wanted to tell you a few words about QWord. Uh, so, as I said, all the educational materials that we'll use were developed by QWord. So it's good to know this organization, good to thank them, and potentially some of you may want to join QWord. QWord is a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and on research activities. So we collaborate globally, internationally to develop the educational materials together. So a few years ago, we found out that there are not enough experts, uh, quantum experts, at least in some underdeveloped countries. So if we want to ensure um, the equal access to quantum education and to contribute to the open global ecosystem for quantum technologies, and this is the main goal of QWord, we need to work together. So that was the idea behind creating QWord. So you can also join the QWord's Discord, follow our social media profiles, YouTube channel, and so on. So it's good to know that QBronze is actually an introductory level workshop. So it's just the first workshop that you can take. Some people take even, let's say, more basic workshop that is called QPrep, but it's not about quantum. It's just so in QPrep you can learn some basics of mathematics like linear algebra or some basics of programming in Python. So this is something like a preparatory course for QBronze. But QBronze is the first QWorks workshop in which you can actually learn about quantum computing, some basics of quantum computing at least. And then after QBronze, you can take some more advanced workshops like QSilver. So QSilver is about um, quantum Fourier transform and Shor's algorithm for factorization. QNickle is about oracular algorithms. And there are also some other workshops. So as QPoland will also organize QThink in November, so it will be about quantum error correction. The workshop on QSilver uh, focusing on the Shor's algorithm and quantum Fourier transform will be in February next year, and QNickle focusing on oracular quantum algorithms will be in March or April 2026. We also organize some hackathons. We also have a research department organizing QIntern. So QIntern is also a very interesting project in which we try to match senior researchers from all over the world. So people who have good ideas for some interesting research projects with students or quantum enthusiasts who want to participate in some research projects, and they look for some research internships, remote internships, of course. And we are also working on the whole curriculum for quantum studies. So at the end of the day, we would like to have educational materials covering the whole level of quantum education or quantum computing education, at least, starting from the basics and finishing at the advanced level. All right, so in QWord we have multiple QCousins. So currently we have more than 30 QCousins in more than 30 countries. So these QCousins are our local operational groups all over the world. So we have about 10 QCousins in Europe. We also have about 10 QCousins in Africa. There are a few QCousins in Asia and two in South America, one in North America as well. So it's a worldwide network, and we want to entangle the new QCousins in the future, of course. So we want to grow, and we would like to engage every country so that people all over the world. So we believe that people all over the world should have relatively equal access to the quantum education. So that's why all the workshops that we organize are free, including this one, and all the materials that we develop are open. And these local groups, like QPoland in Poland, are responsible for organizing workshops for their local communities. But as you know, as QPoland, we are quite well organized already, and we've already organized more than 10 workshops. we've handed out a few hundred certificates, and all our events are in English, so that people from all over the world can join us as well. So that's why actually I think that much more than 50% of participants are from other countries. And if you are interested, you can check the website of our QCousins department to see what are the other QCousins in other countries, and perhaps some of you could maybe entangle a new QCousin in your country, or you can join one of the existing groups. Um, if you like, you can also follow the social media profiles and all the servers, like YouTube channel, LinkedIn profile, Discord server of QPoland as well, and to help us organize our local activities here in Poland. All our local activities are formally supported by Fundacja Quantum AI, which is a non-profit organization. It's a legal entity, legal body, supporting the development and organization of all these uh, events that we organize as QPoland. Okay, so that's all I wanted to tell you. Let's see if there are some questions. Mm, there's a question about access to the Discord channel. So ID, the link to Discord was sent in the invitation email. So please check the invitation email, and there you should have a link to join the Discord. If you do not have it, please send me an email, and I will try to send the link to you. There's a question from Usama. Will you send any link? Oh, I see that Hetanshi has sent a link to Discord. Thanks. There's a question from Osama. Will you send any link for Canvas access? So it will not be a link, but it will be just an invitation from Canvas. So after my talk, I will just give the Zoom to Mateusz, who is our instructor. So he will lead the rest of the workshop, starting from today and until Tuesday, while I will try to send invitations to Canvas to all of you. And yeah, I will let you know on Discord and maybe also here on the chat. All right. Do we have more questions? I do not see more questions now, so let
I
me
think
stop sharing.
we could establish because there is a slot, right, from now until 9 p.m. Time.
Mm-hmm.
We could establish when do we do some sort of a break. I think it would be a good idea to make
To do
such
a
a
break.
break.
Uh,
Yes.
it's up to you, Mateusz. So actually,
Okay.
you can decide later depending on how it goes. Because
Okay. Okay.
I think it's always best to do a break just after you finish some part of
Some
the
big
material,
portion,
right?
right? Yeah.
And
Okay.
then before moving to the next part. Okay.
Okay. Okay.
All right.
So,
Okay.
thank you,
So
Pavel.
Mateusz, yes, the Zoom is yours. I will also make you a co-host, so you can check from time to time if there are some uh, people that should be accepted. You can check it now actually, because I will need to leave Zoom soon. Uh,
Okay.
I think
Okay.
you are already the host, so you can accept new and approve new people.
Okay.
I can I
Accept.
can I can also give. I see that there are also some other mentors with us, like Yusef. So let me. Maybe you can try to also make some co-hosts if you want, or Konrad
Mm,
Wansky.
wait, let me find in
Okay.
the gigantic, enormous list of people. Uh, which okay, I will
Józef
look.
Kasprzycki, for example, or Konrad Wansky.
Okay, there are few Conrads, so I need to find the
Oh,
right one.
would it help if I
Konrad
react
Latsky, yes, Konrad Latsky.
with a clap, maybe?
Mm-hmm.
Here, I'll do this, maybe.
Okay. How
Okay.
can I make it as a co-host because I can
Okay,
make
you can only make
host.
a host. Okay, so
Yeah.
maybe it's not available. So okay, so let's assume that you will be the host, and if you manage to do it, of course, and accept
Okay.
new people. Okay, good.
Okay.
All right. So Mateusz, now the Zoom is really yours. So you can.
Okay.
Yes,
Thank you very
yes,
much.
and
So,
at the end you just need to close finish the recording, of course, and the recording will be saved on in our Zoom cloud, hopefully.
okay. Okay. So welcome today. I will share my screen and we could go share. Okay, so now can you see my screen? That's the most important question. Okay. Yes, you probably will have been blinded just by my white screen that I have now I am sharing. I have prepared a document for today. It will be some sort of quantum computing for beginners, collection of topics, subjects, materials, and links to other resources that should help you start your journey in QC. I started preparing this just before I introduce myself. I tried to prepare this as a very light presentation, but it turned out to be way more than I anticipated. So I will drop a PDF of today's material into the Discord, so you can come back to it. You can read through it at your own pace. There will be a lot about today's day. For example, and some more, of course. So about the mathematical representation of vectors, of tensors, what is the tensor? What are the different different operations that you can do with the tensors, and the probability representations. So this is the day one of today's course. I have prepared most of it in this document. I will generate a PDF out of this, and I will drop it in the Discord for you. But don't worry if you don't get some part of the presentation. But for the first thing, the first thing is that I would like to introduce myself. So with that information out of the way. Hi, I'm Mateusz Anuszewski. This is my LinkedIn. I will drop it in the Discord as well. I have been a Python developer for some time now, and I have started my quantum computing journey about, well, it's like 3 years ago. Since I started my quantum computing journey. This was pretty much when I was at Warsaw at Data Science Summit, and it is a periodic event that is organized in Warsaw, in the National Stadium. So, oh, I have to accept a few people. So this is where I have started my quantum computing journey. So far, this experience is not up to date. I am now employed at the Nexio management company, and now I am in their newly forming robotics department. I would say it is still a Python and AI officially, but it's now about robotics. So now I am at robotics, but about my quantum computing experience, I can show you that I have the diplomas from most of the available courses from QWorld. So, for example, QBronze that I made in 2023, QNickel and QSilver that I made last year. Actually, pretty much bang on last year. So this is like my experience. I then, after the QNickel, I took part in after Silver, I took part in a Quantum Hackathon, which I won at Open Track. I made a game, which was a checkers. I could show you after at the last day of the course. Now I am just mentioning that this is my experience, and there I used Grover's algorithm that will be in this workshop that we are now in. We will do. We will learn the Grover's algorithm at the end. So I used it to make some sort of a quantum computing bot that controls checkers in checkers game as your opponent. So, but this is very simple bot. This doesn't have any complicated logic. I believe that after QNickel, you could also do it the way that I did it. Because this is pretty much based on some sort of quantum if statements. And this is exactly what we will do today and during this course. So we will try to build our knowledge to up to the point that we would learn how to operate on the quantum computing chips, especially from IBM, because this is the course that will be based on Qiskit, which is IBM's solution for quantum computing. So that's about my experiences. I am a programmer for some time now, so I have started in pretty much 2019, and I was pretty much a, let's say, a bootcamp person. That could be a pretty good summary of my experience. So I am self-taught programmer, and this could probably boost your confidence that even you, if you do not have certain amount of experience even in programming, then maybe you also can start in this journey, and you would also be. Oh, I have to accept more people. Okay, here's one person, another person, and yet another person. Let me accept few people. Okay, so coming back to this, I think if I had some amount of success and I am a self-taught programmer, then it would probably the case that you can do this too. Okay, so with that out of the way and with my introduction out of the way, my very brief introduction, I will tell you something about the history of quantum computing. So the first time that I heard about quantum computing was about 2017, when I was a let's say technology of chemistry undergrad, and at that time, for example, when we look at IBM, there is I will link this in the Discord. In the wait, where can I lecture help? Yeah, that could be do. That could do. So I will link this article from 2017. Okay, and you will see that, for example, here is the number of qubits. This is the metric, the main metric of quantum computer is the number of qubits that it has. So like at face value, when you see someone talking about quantum computing, this is the first thing that they do. They talk about qubits. So they at 2017 in that year, there is a quantum computer that had about 20 qubits. There were plans to make this. And I think there is also another number which is 16 qubits or something like that. No, there's 50 qubits in the next few years. So that was the IBM's plan at 2017. they in the future, so in 2018, 2019, they wanted to make a machine that has about 50 qubits. So a couple news, maybe not, that's the wrong word. A couple information about the qubit. So this is a unit comparing to what you have in a classical computer. The qubit is a single unit of information. The qubit is a single like element of the system that carries a unit of information. However, it carries much more information than a traditional classical qubit, the traditional classical bit that you have on your chip, on your silicon. And there are many implications that we will go through during this course that makes this very interesting to process information on qubits. However, there are many problems with qubits that are very apparent once you start processing information on them. In IBM's particular case, the qubits and the machine that they uses something that is called a superconductivity, which means that they need to cool the machine to the very, very, very low temperatures. We are talking about single kelvins or even fraction of a Kelvin. This is how cool they need to get this chip to operate properly. This is incredibly hard task, and oh, if you do not hear my voice, then I could also change the internet. Wait, let me actually change it. I have lack of internet, but it should be better. It's fine for me as well. Okay, okay. But I will switch to it if this will be the case. Okay, so oh, Kevin is also okay. So back to our discussion. The qubit is an element that can process information, but as we said, to recap, this needs to be very cooled very, very heavily to work properly in terms of IBM's solutions. There are certain parts of the chip that does this information processing. For example, you could look at the part of the circuit that is called a Josephson junction. And I will link this Wikipedia article in the Discord for you. So this is the part that does most of the magic. It does not do all the magic. It does most of the magic. And oh, I am unable to join the Discord link. I do not know if I could fix it, and I would like to not do this in the middle of the lecture, so I will do it after my introduction to like most of the things that we will do. Okay, Honey, Mr. Honey, Mrs. Honey. I don't know. I have only Honey here. Okay, Miss. Okay, so. So this is the element that does some magic, actually big part of the magic in the quantum chip. There are some implications to the layout of this, but we will talk about this slightly later. The most important thing is that you cannot cool this machine very well most of the time. And this introduces bugs in your circuit. So, or rather bugs in your computation. That's the most proper way to describe it. There are some errors that are introduced through, for example, thermal effects that happen on this chip that, let's say, flip a bit from 0 to 1, or flip some sort of a phase. We will get to it in the future lecture, why this matters and why there is a difference between something that you may not at this moment know, which is a phase, and something that you probably know, which is a bit. So these effects do happen to mess up the calculations. And during the development of these chips and progression, for example, in 2022, when I met Paweł, they had a presentation and they had a road plan of the IBM in the future years from the perspective of year 2022. And what they achieved at that time was that they had achieved circuits that had, for example, 130 qubits. I believe that this chip architecture was called Eagle, but I am not exactly certain. IMB, yeah, IBM Quantum. That's Quantum Computing Home. Let me see if I can get this architecture. Maybe I will present it tomorrow. Yeah, so look, now you have 100 plus qubits and you can start for free. That's the best thing that you can probably, that is the outcome of this 10-year effort, close to 10-year effort, 8-year effort, or even back, because like what I have presented to you is how, from my perspective, but it started all way sooner. And in the next lecture, I will tell you some more about the actual origins tomorrow, and some of the operations that what scientists at first have discovered and how it progressed further. Now I am talking to you about the architectures, the most of the initial information that you would probably need to know, the state of it today. And tomorrow we will talk about how it was in the past and where this weird information, quantum information, came from. So yeah, so 2022, 127 qubits. This is the Eagle architecture. I believe that was the name. And now there are even architectures. There is, by the way, QWorld Discord. I think I could drop you an invitation to this Discord, because this is the main Discord for our entire organization, QWorld, and there is also a QPoland Discord that I will also link you in our Discord, in the Discord of the QBronze166. So what I have pretty much read yesterday or 2 days ago was that now there are efforts to make machines that are, let me find the link, because this is actually ridiculous. Articles, and now, no, not articles. Q News, yes, that's it. Look at this, 6,100 qubits, okay? 6,100 qubits. That's how much qubits we now are trying to like harness. That's the right word. So that's insane progress. For why does it matter to have this many qubits? recall my information that it is very hard to control qubits because we have to cool them to very high temperatures. Very low temperatures. I'm sorry. There are actually methods to use these qubits, these 6,100 qubits, and tailor them into specific, let's say, perform a specific computation on them to harden them against these errors that happen on our machine. This is called quantum error correction. There is another branch to it, which is called quantum error mitigation. This is like the difference is basically that quantum error mitigation focuses on very easy, very cheap methods to increase the fidelity. Let's say I like this word to describe it. Fidelity, which means correct answers to our problem, and through the quantum computation, and repeatable. But the quantum error mitigation, for example, throws in extra operation here and there, or focuses on shortening the total length of the algorithm, or something like that. Quantum error correction focuses on developing entire algorithm that is devoted to decrease the error rate of your calculations. And unfortunately, by doing this, you have to spend a lot of real, what we call physical qubits to tie them in the special, like, I would call it a structure, but that's not the right word here. That can be a right approximation, I think. And we tie them in the certain structure, and then the structure, this weave, because there are algorithms that tie them in the surface on the chip. And what we need is literally hundreds of these physical qubits to create something that we call a logical qubit. So what's the difference here? The logical qubit is the qubit that has very, very, very low error rate. For example, 10 to the negative 10, right, in the exponent. Meaning that we can have dozens and dozens of operations, and it is very highly improbable for us to have a single error, even a single error. So yeah, so that's the main effort in the quantum computing nowadays, to increase the number of physical qubits and then to tie them in this structure to form a one or couple or dozen logical qubits, and then do calculations on these logical qubits that have very high fidelity, very low error rate, and then we can solve business problems on these logical qubits. Yeah, so that's pretty much it. To recap all what I have said, again, from yet another perspective, we need more qubits, more physical qubits, which means that, for example, more specific structures on the chip to perform better calculations, more reliable calculations to solve problems that are seen in business. Okay, so now you might be thinking, okay, that's one phase, that's one side to the problem. That's one side to quantum computing, right? You have the hardware, you prepare it, make it better to, let's say, solve these business problems. But are there actually any jobs that we could probably, oh, more virtualization with regards to logical qubits? I will link a paper later, and you could make sense of it later on. This is maybe not not some kind of virtualization, because this is mostly this is hard to explain, because I have not done these type of calculations, so I cannot find proper words to describe it, to describe this process. But what you do is it's not virtualize. You perform calculation on physical qubit, on 2 qubits, then on 4 qubits, on 8 qubits, physical things that are on the device, okay? And you tie them through these calculations. And when one thing, and when one qubit errors out, you have way more physical qubits to correct this one that errored out. So this is not virtualization in the classical term that, oh, I throw another machine in terms of, for example, throw a Docker container or something like that. Or maybe you could say that this is also not something like bare metal. Not really. This is more like mathematical tying the physical bits, that could actually be good. It's like as if you have a mathematical operation that you realize through assembly instructions on your entire register in, let's say, your Intel CPU, because your Intel CPU pretty much errors out and flips bits randomly. But through this assembly language, you can tie different bits together and realize a protocol that even when you have like a single error with single bit, you can recover this bit back. This is what I mean with quantum error correction. This is pretty much what you can. How many logical qubits are there out of those 6,100 physical ones? That's a good question, because this is a very fresh breakthrough. Look, this is from pretty much 2 days ago. I do not know what they did. Really, they only these are researchers from Caltech, I think. No, California Institute of Technology. Oh, Caltech, yeah. Sorry, I think that's the shortcut they use. So I do not know what they did exactly with this 6,100 qubits, but in these algorithms, you have to tie hundreds of these physical qubits to get one logical one to perform good calculations. Okay, so what types of particles are typically used to create qubits? That depends on the machine. There are no right answer. There are some, oh God, that's a very hard question, because usually we do not do any sort of introduction to quantum computing hardware during these courses. So I could be mistaken, but usually this is a line of single atoms, for example. If I read this right, this was an array of atoms. Okay, I cannot find this. I cannot find this now. I wouldn't like to pause the entire lecture to extract this information. I'm sorry. I will get back to you with this answer. Cesium atoms. Okay. So that depends really. That really depends. It can be a single it can be single atoms. It can be entire particles. That does a state switch in some sense, and it is pretty much tied to exactly the quantum hardware and the producer of this quantum hardware to how to with what are the calculations performed, what are the actual like quantum gates or something like that applied, and what are the what do they mean in actual physical world, right? So it could be, for example, beams of lasers that are tying these different qubits together through some process, right? Or something else completely. That really depends on the hardware and to whether you, for example, even perform calculation on light or not even atoms, like light also. I think I heard that Xanadu, which is a actually this is a good moment to go through this as well. So Xanadu has different hardware that is based on processing, for example, entangling light particles, right? And speaking of different hardware manufacturers, now it could be a good idea to actually tell you about different, let's say, not only manufacturers, but also different, let's say, how do I put it? Differences between, um, let's say, the differences in the state of the software. Because one thing is the actual hardware, and hardware progression is very, very meaningful in this field, because we are at the age of pretty much quantum computing assembly. But this changes as we speak. So now it is good to actually go to one of the resources that I have. So I told you that there's this resource that I have prepared, and there are different workshops that we have, right? We have different we have QBronze, QNickel, QSilver, and QCobalt. Uh, there will be links in this resource in the PDF that I will generate. And what do these mean? Well, first let's say a thing about the software, which is different types of frameworks that you can use to start your journey. Uh, in this workshop, we will use Qiskit. This is IBM's solution, but it is not only one that is out there. And this is the most frustrating part, I think, out of the current landscape of quantum computing, because you have so many frameworks from so many different manufacturers. For example, uh, there is Penylane. It is from Xanadu. I just briefly mentioned it, that they have their hardware based on, for example, entangling and making operations on photons. There is Mind Quantum, which is also available as a QBronze, another type of QBronze like a workshop, but specifically made in mind with the for example, Mind Quantum, Project Q frameworks. And these are the companies that are behind these solutions. So Penylane is made by Xanadu. Mind Quantum is by Huawei, and then Project Q is by Mindspore. There are more. For example, the one that is not listed here is D-Wave, and they have their own package. D-Wave Quantum. they have their own type of hardware and they have their own type of software that interacts with this hardware. So like when you look at this and you try to convey some information for yourself, or maybe you want to get some experience, you are in bad luck if you want to get into this on a face value. There are some other solutions, however, because what these frameworks do is they are like the let's say these are like the building blocks, but for only this one quantum computing manufacturer, quantum computing hardware manufacturer, right? For example, IBM works on IBM, D-Wave works on D-Wave, and so on. There are some other solutions. For example, one of them is Classic. This is a software package that aims at performing calculations on many hardware, let's say many hardware manufacturers, without you worrying about this. Okay, so you can design your algorithm in their software solution, in their framework, and as you can see, there are many trusted partners. And what they do is that you can do it with their, I think, because I didn't actually use it. What you could do is you could log into their site, do this through their website, and I think you could even arrange a job. You can submit a job on actual quantum hardware from your choice. It could be, for example, IBM, for example, D-Wave. You could select it and run your quantum computing circuit without worrying about this issue that I have stated. Right? I don't think that there is any layer of translation. For example, let's say, oh, you already have written something, and let's say that I want to let's say that I've written something from IBM's solution, and now I want to run on any other quantum hardware. Is it available for this package? I also am not aware of this, but you could try to, after this workshop, you could try your luck with this solution, and then you probably wouldn't need to worry much about the differences between the packages, because this library, this software will do it for you. So this is very big advantage of using their solution compared to the factory specific, let's say. So that's very nice from them. What else can be said? Okay, so we have talked about software. So now what about different differences in the experience levels? So I have prepared this right before this lecture. There is quantum computing progression chart. What I wanted to convey in this chart is that there is some sort of a starting point. There is some sort of progression path for you. For example, you could choose you have chosen QBronze. This is, I think, very well, very good choice. There are other choices that you could make as a beginner, and there is one that is linked in a QWorld. I think I have seen this. Yes, so this is the one. This is another one. So this is Adequate from QRECA. This is also a end-to-end quantum computing technical course with the QWorld partnership. and this is for free. I think so far, when I have seen this from Maya here in our keyword Discord, this workshop or this course is available is available without a price tag until the end of December. So free until the end of December. This is what I get from this message. I don't know what would be the price of it later, but you have 3 months to actually like certify yourself apart from doing the QBronze course and all of the courses that are directly made by QWorld. So I will link this in the Discord in the QBronze166 in the lecture help as well. I have just posted it, so you could check this at your leisure later on. Okay, so what else? This is entry level. Actually, this Cureka course seems to be from literally like fundamental all the way to quantum machine learning. So there is quite much more than what we will be doing in the QBronze today. So that's one thing. Okay, so what about experience? Because we have been talking about beginner. QNical and QZync, that would be the next step, I think. I cannot talk much about QZync because I didn't take it, but I have taken QNical, as you probably have seen from my LinkedIn, a page that I have just showed you. This focuses on Grover's algorithm for graph analysis. QNical is like expansion on QBronze, and in terms of material, it is a very direct expansion because what you get is to perform slightly more advanced calculations, and for example, more diverse, let's say, uh, instruction creation and management during your quantum computations, because there are many instructions that you could make. For example, you could package them in certain batches, and you could compose these batches into way bigger batches, and you could assemble your algorithm like this. Instead of listing instructions after instructions after instructions, I could make a sub package of instructions and append it at the end of my algorithm to expand it further and further and further. And with many calculations or with many instructions, this is the way to go. So you are introduced to it during QNical. QSilver is expansion into, for example, more into how do I express it? Expands more on top of the quantum nature of the calculations, and you get further in your algorithm knowledge. For example, there is quantum phase estimation, quantum Fourier transform, quantum counting algorithm, and as a result of quantum counting, you have Shor's algorithm introduced. So if you want to break ciphers, as quantum computing was made famous by this algorithm, because previously before Shor, it was like, yeah, we could do something, but it's like, does it really help me here and with anything? The Shore was a game changer in terms of media presence, because now it's like, oh, we now can break security. Okay, that's big. So this is what you could learn from QSilver. QCobalt, quantum annealing, it is used pretty often, but I cannot tell you much about it. And QTitanium is something that isn't really listed on keyword pages, but I have seen it through other Q class 2324. So they had, so Q class is like a compound type for compound type of quantum computing courses, composite of different quantum computing courses. And this is for example, undergrads. And what they do is introduce you to many more different, let's say, many more different subjects than what we will be discussing throughout this series. So yeah, so that's that. And Q Titanium is topological quantum computing. So that was about courses and certifications. What else can you do? There are events and hackathons. There is, for example, I believe on 10th of October, there will be, or 11th, 11 and 12 of October, there will be a quantum machine learning workshop. I do think that it will be about quantum annealing. So if you want to know this, there will be some mention of this algorithm and how to perform it. QPoland Global Quantum Hackathon is also a good opportunity to test your knowledge. I have participated in QPoland Quantum Hackathon with the knowledge of QBronze and QNickel. So this is doable, really. And there are other sources, for example, Dora hacks. This is a nice page. This is a, let me, Dora hacks. Let me open this. So this is a page that unites most of the hackathons together. So there are many hackathons about AI, about blockchain, and also about quantum computing. Some of the competitions are there made with this in mind. So you could search this page. I will also link it. And you could search this page, and whenever you feel ready, well, or even not, or even after some time, or when you find a partner, just go and give it a shot. What do you what do you lose, right? So you could give it a shot and search for a quantum computing hackathon. There, you could get some RENES experience. Maybe you will win, maybe you will not win. That's all up to you. I think you will get some good project to your portfolio by participating in such hackathon, right? So here's the short track that I have picked. So QBronze, QNickel. I think I have actually I have to swap these because I think QSilver was first, then QPoland Quantum Computing Hackathon. Yeah, so that's most of the information about the courses, certifications, how to get knowledge. I have introduced you to quantum hardware. So the last thing about to give you the entire picture of the quantum computing sphere would be the jobs, right? The job security. This would be the next step to talk about, to complete this, to complement all of this, what we have been talking about. There are different pages, and there are different I'm sorry, pages. There are different quantum computing positions that you could strive to be in. For example, what I have seen is exactly this. I was actually amazed by, for example, Rolls-Royce, that needs that posted a job opening. This is 8 days ago, so this is fresh. Quantum computing specialist. Okay, what are the let's say the requirements? There are different. There are two different types that seems to be common. One is for algorithms and different solvers, development of different solvers. So this is literally this. I will make this a little bit larger. Quantum linear equation solvers. This is a job for someone that graduates from physics. And quantum chemistry is mostly doing, since we are involved in quantum computing calculations, what we do is pretty much literally do what's happening in actual physics, right? So if we could calculate information on a quantum computer, we could probably do something to, let's say, predict a new material structure or propose a different structure for the material based on these calculations. Here they list that using Hamiltonian evolution and mesoscale optimizations for material properties. So material sciences. This is another position that is very common, and I see it pretty often. I think I have seen about 2 months ago an opening from Microsoft, which also was about something in between, I think. I have to find this. I have to find this page. Maybe I have something in history. And look, essential skills. Well, a degree in physics, mathematics or equivalent, but also Penny Qiskit Classic. So this is literally what's being listed, right? And experience in C, C++, desirable, magic encoding, updated amplification. Yeah, machine learning, parallel programming, HPC. So this goes in complement together in tandem with whatever they list on their job listings. So there is definitely something that is happening. There are other sources of job listings. That's not the only one, because you could probably say, oh, okay, you have said you have listed like a single job opening. Okay, what about others? You could subscribe to some job listing newsletters. I think I am on one. I will show you this tomorrow because I have to dig this out. And or after short break, we could actually make this one now if you want. Because there was a lot of information that I have that I have told you right now. So if you need a break to chomp on something quickly, then we could process the rest of the information for today. Yeah, so I think you have enjoyed my introduction to quantum computing, the overview of the entire space, and yeah, so let's take a break. We could do it until let's say 19 hours 20 minutes. So like, or maybe you know what, let's do it 7:30. So 15 to 20 minutes. Let's take a break now. Let's take something to drink, something to eat, and we'll be back after this break. Okay? Okay, right. So I will mute myself and let's take a small break. Okay, so the hour is now at the exact point that we have discussed. So is everyone ready to progress? Or are there any questions to today's lecture so far, to whatever we had discussed, whatever I have told you about? Oh, are there any questions? Damien here has asked, can I send today's slide during the break? I have already did that. Oh, maybe this will do because I had my microphone out of the way, okay. So small recap, right? So we have discussed first. First, I have introduced myself. So that part we can leave out. Then I have begun explaining why the hardware improvements are important and what are the hardware improvements, what are the challenges during the during the improvement process of the hardware. Let's say that we have architecture that depends on superconductivity, and the qubits need to be cooled to very, very low temperatures, like fractions of a Kelvin, above absolute zero, and that even then it is very hard to cool them like that. There are errors that then require us to prepare special algorithms that tie these qubits together. And even then, when we increase the hardware qubits, which we call the physical qubits, it is not the same. And we also introduced the term logical qubit, which is what we want. The logical qubit is free of errors or very close to free of errors. So the hardware improvements can give us more physical qubits to work with, and then we can tie physical qubits into a single or an array of logical qubits that can help us solve the business problem. So that was about hardware. Then I have spoke some time about the software, and I tied this to giving you a roadmap of increasing your personal experience. I told you that the software is very tightly intertwined with the progress in hardware, and every hardware manufacturer has its own software package to interact with this hardware. For example, IBM, which we are getting knowledge in this course, has a software package called Qiskit, and we will be using it throughout this course. But this is not the end. There are many more. There are many more software solutions. Like for example, D-Wave has its own software solution. There are other software solutions that I have listed in this part in QBronze. There is Penylane, there is Mind Quantum, there is Project Q. The Mind Quantum and Project Q are also available as a QBronze materials. So that's that. And there is also this other software package which is from Classic that aims to be hardware agnostic and aims to deliver you certain algorithms out of the box. So that was the second part of my quantum computing ecosystem overview as a recap. And the last part of the recap was job security, right? I did spoke only a little about it because I am not that well versed in this type. But I mentioned that there are job openings for it. I mentioned what are the requirements for the job openings to fill them. What do you need to fill them to secure yourself a job in this field? And also what I mentioned is how to find these jobs. So there are some sources of information. For example, ORNL job listing. I did not mention this exact piece of information previously, but I mention it now. So I will try to find the link for their newsletter, but this is like you have to get an invitation from them. This isn't very hard, to be honest, and they usually accept everyone. But this, I think, to get rid of some of the unwanted guests, let's say bots, I believe, or something like that. I don't know why do they do it like that, but they do it like that, really. And monthly or something, they send you an email with the job openings or something like that. So that was the last part of my quantum computing overview. Yeah, so that's that. So we have talked about this. We have talked about how you can progress in quantum computing knowledge. I have showed you my progression. So it was QBronze, QNickel, then QSilver. I have wrong ordering. Then QPoland Quantum Computing Hackathon, which was actually hosted on DoraHacks. I have told you about DoraHacks and that you can join some of the quantum computing hackathon event that they organize or is hosted on their page. And that's it. That's the end of the recap. So now what? We are left with the actual material of QBronze, which is going to be a pretty much conducted throughout the course with the help of Jupyter notebooks. If you did not, I think that most of you have interacted with it, but if you did not, then on the Discord there is a installation help channel, which you can ask questions. There is a installation link linked by Roch, and what he had showed is the PDF link to the actual like QWorld QBronze166 link from the repository, and there are installation instructions for the, I believe, Conda together with, yes. Yes, so there is everything. I believe there is everything. So first you install Conda, you set up Jupyter notebooks, and then after you download the actual repository, whether it will be as a zip folder or as some sort of Git clone or something like that, that doesn't really matter. What matters is that you run a command inside of the Anaconda prompt to install everything with the use of their YAML file. I believe it is when I go to the home and QBronze166, there is an environment.yml. This is what you use. There are, and the Conda environment will set up everything and install everything for you. So that's that. Or you could just plain go with regular Python installation and go with the route of creating a visual environment yourself and doing it through the requirements.txt file. That is also included inside of the actual project folder. So yeah, so that's that. And now what we have to go through is the basic mathematics. So basic mathematics is also covered through my resource, so I will go through it very quickly. I'll just present it. It isn't anything that we should worry about, I think, because this is basically pretty much about vectors, linear combination, as you can see, and so on. But let's be complete. That's the resource for the QBronze day 1. So let's start with the vectors, and then we will go through other elements. So first, the vector is an element from the vector space. Vector space is a mathematical object that is a sort of collection of items of this type of vectors. And vectors have different components that are expressed by numbers, which are pretty much kind of like a pointed stick in the space. We could think about it. There is a definition that we will get that will arrive at slightly later on. But this can be represented as basically this. Full list of the operations that can be done with the vectors is on Wikipedia. I will not go over like defining the zero element that is in the vector space, and that is zero vector, and so on. Multiplication by scalars is defined slightly later on. But there is one very important consequence of existence of the vector spaces and elements of the vector spaces, which is linear combination. Linear combination is incredibly important, and it means that we can add vectors together, which is pretty much, you could visualize it as a tip to tail addition. I have a visual representation of this slightly below. But first, we could add the vectors together like this. So we have a vector v, and we could define it as being composed of different other vectors from the same vector space. So from the elements that are alike, with some sort of combination based on addition, basic plain addition. And there is, for example, a k vector scaled by coefficient a, l vector scaled by coefficient b, and m vector scaled by coefficient c, and so on and so forth. The ABC are scaling coefficients, and k, l, m are the vectors that are composed from this into the vector v. Oh, there are some people that want to join. Okay. So then, how is actually vector expressed? Vectors are expressed by some elements from that vector space that are, let's say, basic to this space. Let's say we do this kind of like defining a 1, and then we compose all the other numbers by, for example, adding 1 successively, and so on. So what happens in the vector space is that we add together various of these ones in different directions. And these ones are called basis vectors, which are expressed here in a column notation. So this is like a list of numbers, a list of real numbers. And each basis vector, the most convenient notation is that there is a 1 in the space in which in the direction that we go through. If we go into different direction, for example, into left, right, front, back, up, down, there are different vectors that express this translation. So this transition, and we define the basis vectors for each of these dimensions, what we call, and we compose vector in pretty much a linear combination of these basis vectors with some scalar. Right, as you can see in this picture. So I can compose V as a linear combination of many different vectors, but what is most let's say what is the nicest for us is as if we have, oh, there is some yellow line. I don't know what's happening. So it's the most is the nicest if we have if we express this combination of that this vector is composed of from basis vectors, because basis vectors are like, okay, I need to take X amount of basis vector in this direction, in its own direction, then a Y amount of another basis vector in another direction. Let's say this would be like right, left, and Z amount, which is yet another real number, in yet another direction, which is, for example, up and down, and we compose the vector in this form. This is very nice and easy, and we could shorten this notation, and we could completely avoid writing all of these different columns of zeros with only a single one by either making it like this. So V equals X EX, Y EY, Z EZ, or even more simple. And this would be this representation. So each vector could be added together with the other vector in this form. So x1 plus x2, y1 plus y2. And if we combine this vector addition with this very simple vector addition like this, we could see an analogy of having our vector being expressed as a column of x, y, z, t, and so on and so forth. So this will be so this column vector notation will be very standard throughout this QBronze course. There are other notations. For example, there is a notation that represent all the vector components, because x, y, z, and t, and so on, are called vector components. So these are coefficients that scale every basis vector, as I have listed it here, that scale every basis vector from one vector to each other. So this notation will be the one that is default. There is yet another twist to this. So in this material that you see in being presented to you, uses a square brackets to as a representation of the list of vector components. There is also in the QBronze materials, there is also a notation that uses a round brackets, not the square brackets, but the round brackets as well. I prefer this notation. This is what I am used to, as from matrices, which I will introduce shortly. But this will be the prevailing notation for our vectors from now on. So that's that. We have vector with vector components that are real numbers for now, that will be listed as a column of numbers, which means that, for example, we go x amount in one direction, then y amount in the other direction, and z amount in the yet another direction. So this was very short introduction to it, but there are also way more things that we will not go through in this QBronze course. There is a very good resource for it. I have linked this in the first slide of this presentation. There is Tensors for Beginners from Eigenkreis. This guy is really, really good. And this series for Tensors for Beginners really touches on whatever we will do. And the linear algebra, which means the operations on vectors and on other elements of other spaces by Freeblue Brown, Linear Algebra Explained Visually series, is also incredibly good. Both of these are very hard to beat. And if you want to understand something from my explanation, you probably could understand something from their explanations as well. So this is like another direction that you might go to. However, from Tensors for Beginners course from Eigenkreis goes way, way, way deeper into what tensors are, and we won't go as deep as he will in this course. But he also explains many of the subjects that we will touch upon throughout this course and operations. So I explain vectors, what they are. So vector is a member of vector space that has certain components which tell us in which direction that this vector points at. Like, for example, here. So this is a slide from the presentation of Eigenkreis. I believe this was from the episode 0 of his series. This is very good explanation for very good basic explanation. So the vector is object that is invariant under a change of coordinates. So a vector is also called something that is a tensor, and tensor is way more expanded definition of what we will do in this series of lectures, and this is way more generic, and this describes way more than just vectors. Because, for example, here a scalar, which is a single number, can also be described as a tensor of rank 0. Or vector can be described as a tensor of rank 1. Matrix as a tensor of rank 2. And there are way more tensors that we could see in during the calculations of different things. For example, here is rank 3 tensor presented visually, let's say. So you can say that, okay, why we don't use the way more simple definition, which is the multi-dimensional array of numbers, or grid, as exactly the Eigenkreis says in his video, his episode 0 video. Why we don't use this? Well, we don't use this because the collection of numbers doesn't really tell us about what this collection of numbers means and what is its geometrical meaning. This will be very important for us later on, especially on the day 3 onwards. Day 2 not so much, but we will also touch upon this on the geometric meaning of different, let's say, objects that express our operations on quantum states. they will have certain geometric meaning in the space that we will talk about. And the multidimensional array of numbers or multidimensional grid of number definition doesn't really express this very well. So that's why we say that a tensor is some sort of object that is invariant under change of coordinates, whatever it means for you right now. And what does it really mean? Well, let's say that we would like to express our space differently. Usually what we do by expressing the space differently is we change the basis. And change the basis means that we can describe our vector with the vector components somewhat differently. For example, different components in this case are, let's say, in first basis are yellow arrow, green arrow, and blue arrow. And the pencil here, which is our vector, is described as, okay, I take two yellow vectors, one green vector, and two blue vectors. But what if I change the basis? So now, after I change the basis, I can say this. Okay, after I add two black basis vectors, three purple basis vectors, and one red basis vector, I get the same thing. But now I have way different components of this vector. So components do change. The vector itself does not change because it still expresses the same idea, which is in this particular example, it is pointing at the closest door. So that's what we mean that the vector is invariant. The vector itself is invariant, but it can be expressed by the different numbers once we provide us how we get to this expression by providing also the basis vectors in which we calculate, which is like a template. Oh, this is how I got to this result. This is how I point at the door in this when I express it this way, and this is how I point at the door when I express in another way. Right? So that's what I mean when the basis is changed through a process called the change of basis. There is also another elements that are required to do this change of basis, and that these are special matrices, which is the two-dimensional arrays of numbers, what I do here, but they do have a geometrical meaning, which is that I express these matrices are forward and backward transformation. And what they do is they allow us to geometrically express that, okay, this coordinates of that this vector components of this vector, when I transform them into another basis, this is the correct answer. All right, this is how these two vectors from these two different bases, after I transform them with that explicit matrix, these are complement to themselves, and they express the same thing, even though they are different numerically. So yeah, there are different. So that was the linear combination of vectors, right? We said that the two yellow vectors, one green vector, and two blue vectors, which could be expressed, which could be expressed as, for example, 2x, 2ex, 1ey, and 2ez, which means the 2ex basis vector, a single one y basis vector, and yet another 2ez basis vectors express my thing pointing at a door. This was a linear combination of vectors. What about something else? Can I arrive at the same thing when I do a linear combination of not rank 1 tensor, but rank 2 tensor? And it turns out that yes, there could be a linear combination of some other elements. Here is, for example, a linear combination of matrices, and it arrives at this nice matrix ABCD, which is like 2 by 2 matrix. This is sometimes called a linear map, and this is an operation on matrices which are rank 2 tensors. As you can see, as you can hear, I use these definitions. I go from one definition to the other to get you used to these two definitions. But this is what it's like. So you could come up with addition of not only vectors but also of the addition of matrices. Also, what I snuck here is something that I have on the yet another slide, which is scaling a matrix by a factor. So, for example, what I here have is a very simple operation of I have a matrix with only a single element that is 1. How do I scale it? Okay, I apply a scalar onto a matrix, which is pretty much a real number, and I multiply it like this. So I have a square matrix, and what I do is I multiply this 1 by a, which leaves me with a only. But in general, what I could do is also I could express it like this. So I multiply it by some scalar s, and now I have more complicated matrix, which is a, b, c, d, as we have seen previously, and I incorporate a scalar onto each element. So this is how you scale a matrix. And the same thing you can do with the same thing with the vectors, which are rank 1 tensors. So if I scale the vector by some scalar, which is here some real number x, then this x gets incorporated into vector like this. Here, as you can see, this is what I have used previously to come up with our example up above with this one, right? I have come up with this vector, with this column vector of x, y, z, and t by combining my basis vectors scaled by y, scaled by x, scaled by z as a linear combination like this, using what I present to you here, right, in this simple case. And in general case, I could scale entire vector by multiplying each of the components by the scalar s, like this. So I multiply it by a scalar, which is also a real number here. But it can also be a complex one. So what else? So I have told you about the scalar multiplication and about linear combination of different elements, right? Which is pretty much definition of addition. What else can we do with these elements of vector spaces, which are vectors, and what I can do with tensors of higher ranks? I could do an operation that is called transposition or transpose. So I could take an array and transpose it. Or, sorry, I could transpose a matrix, rank 2 tensor, or I could transpose a vector, which is rank 1 tensor. What do I do here? In terms of vectors, I represent it horizontally, but it is a completely different element, and it doesn't, and in other operations, it does not serve the same purpose now. In terms of matrices, I see the diagonal and I flip the order across the diagonal. So I swap the places of all the elements, as you can see here. For example, SA and SD are the diagonals. And I swap SB and SC with each another. Oh, there's another person that wants to join. So that is an important operation to know. You might say, why? Well, there are other more complicated operations, and transposition of the either array or matrix, I'm sorry, and the vector affects other operations. For example, we have a multiplication. Here, the star is slightly bad notation. This is multiplication. This is nothing to do with what we'll be talking in just a minute. Treat it as a regular multiplication. So what you can do is you could actually define several different types of multiplication depending on what your input is. For example, you could say that you do a naive multiplication, which is also defined as element-wise one, which is that I take each element from one tensor and I multiply it with the corresponding element of the other tensor. What do I mean by corresponding one? Well, here we have a good example of this. So if I see that I have an element in row 1 of this tensor rank 2 and column 1 of this tensor rank 2, I perform a multiplication with the element of the with element from exactly the same column and row from another matrix or another rank 2 tensor. I want you to get used to me saying different terms. So as we can see, we only multiply A11, B11, and the result matrix is that in row 1, column 1, I get multiplication of also row 1, column 1 of the previous two matrices, of previous two tensors, because what you could do is also do the same for vectors. What are the conditions? Well, in terms of vectors, it would be that these vectors have to have the same number of elements. But in terms of rank 2 tensor, they have to have the same dimensions, so the same number of rows and the same number of columns. And the element is the result of exactly what you see here. So multiplication of all the only the element that is corresponding in both matrices. What you can also do is invent an even another type of multiplication, which is called to be a standard multiplication, standard matrix multiplication. Here, what we do is quite different than what we did previously with than what we do with the Hadamard product or element-wise multiplication, because we take the column. If we say that we multiply A and B is the second operand, and A is the first operand, is we take when we want to see the result in the first row, the first column of the resulting matrix, what we do is we take the first row of the matrix A and the first column of the matrix B, and then multiply each of the elements with the same index and sum this together. So that's the definition. The definition here is like this. So we take most of the we take the each row for each element. I'm sorry, for each element of the resulting matrix, we take the row from the first matrix, column from the second matrix, corresponding to that place of the resulting matrix, and we multiply them element-wise together. So that is how a standard matrix multiplication is defined. And there is a condition, one condition, which is quite a different one compared to the naive multiplication, which is that the amount of columns of the first matrix have to be exactly the same as the number of rows of the second matrix. So the number of rows and number of columns have to match in a very specific way. And if you notice the definition, it kind of makes sense because we have to have an equal number of elements in the first row and the first column if we want to make a first row, first column of the result matrix. So because otherwise we don't have the pairing for this. So that's really logical in terms of that. So in terms of the naive multiplication, what we could do is usually there could be a very nice speed ups in hardware, for example, using the AVX instruction set, which is a fancy way to say that you could perform a single instruction multiple data operations on your CPU to arrive at the element-wise multiplication faster. And in terms of the second matrix multiplication, well, there are some nice algorithms for this, but it is way harder to come up with something really fast. It is a field of constant improvement, even nowadays, to find better algorithm for the standard matrix multiplication on the bigger cases. So if you don't really remember, as I am always forgetting these conditions for those operations, I have a single paragraph that sums the required conditions for both of these operations. So if you will get lost, I have these summed up in 2 sentences. So pretty much element-wise multiplication takes in 2 matrices or vectors that have exactly the same layout of elements, and in standard matrix multiplication, the number of columns of the first matrix must equal the number of rows of the second matrix. So that's the takeaway from these 2 different multiplications. Okay, so slightly more about multiplications. So why is it so important? Well, it turns out that for example, when we swap the order of operands, we get slightly different results. In terms of standard matrix multiplication, here are two examples that I come up with. Very simple ones. We have a single element in each of these, single non-zero element in each of these matrices. This first multiplication is AB, second multiplication is BA, and as you can see, we arrive at two different results. So what we say is that it is not it does not preserve the same result during the change of operands. So it's very important to be careful about this and to multiply in correct order the way we want. Yeah, so that's one thing. Okay, but what about, for example, a rank one multiplication? Well, we also have some special cases, because let's say that we can come up with a matrix multiplication of two different vectors. Here, for this matrix multiplication, what we use is the transpose of the vector. If we take the vector and its own transpose, what we can call this operation of vector transpose multiplied by vector with itself, in quotation marks, we define this special operation as an inner product. So what we do is actually what we come up with is a single scalar as a result, because look what we do. What if we come up with this definition from the standard matrix multiplication? We have only one row and only one column. So if we kind of mock the standard matrix multiplication formula, we would arrive with a matrix with only a single element. And this element would be a single number also. So we could drop these brackets, these square brackets, and we could say that, okay, we got a scalar, we got a single number. And what does it do? How we define this is as an inner product. And we multiply pretty much all the vector components with one another, respectively. So we multiply x with x, y with y, z with z, t with t. For every single component that the vector has, we could define inner product like this, as v transpose multiplied by a v. So what is actually, why this operation actually, what does this, what is that operation? What does it tell us actually? This operation actually has very nice connection to Pythagoras theorem. Because what we could do is, well, here's exactly that. So we do a linear combination of vectors. We have b, g, and y vectors, and r is our output. But what we can say about this r vector is that when we perform an inner product and square it, we could get something that we call mathematically as a norm, which is a length of this vector in space. And this is actually a very nice connection to the Pythagoras theorem. And this is something that we get when we pretty much define an inner product. However, what we could do is something that, well, okay, you said inner product of vector with itself, but what about if we literally, let's say, select another vector, a different vector from a vector space? Does it mean that we can get the same result? Does it mean that we get, I don't know, a Pythagoras theorem of both of these vectors at once, and that's the result? Well, not exactly. There is a very nice result of the, let's say, inner product when we take two different vectors from the same space. So remember, they do need to have the same amount of elements for this to work. And what we can say is that this element-wise multiplication can give us different results. For example, one of the very distinct results is when we, out of this operation, we get a 0. What does it mean? It means that we actually have no common components with each of these vectors, and we say that these two vectors are orthogonal to itself, to themselves. For example, one of these examples of orthogonality are our basis vectors. That's why we are. That's why we actually select them as that, as 1, 0, 0, 0, 1, 0, 0, 0, 1, because we would like them to be orthogonal to itself, to express fully that we move in certain different direction, and we get them to be quote perpendicular to themselves or orthogonal. Okay, but what if they are not orthogonal? What if actually our inner product have some result? What does this mean? Well, it has a very nice connection, and what it means is what it helps us describe is, by this real number that we get as a result, it can sort of give us an idea of the overlap between these two vectors, or rather, more specifically, the angle that these two vectors form in space. When we form an inner product of two different vectors, we can get some real number from it. For example, here in this example, in this document, I have set it to be 49. These are two vectors that I have picked. When we divide this 49 by the norm of these two vectors, we get a fraction. And this fraction can give us the angle, the actual angle, when we combine with arc cos function. Here I actually converted this into degrees to have it slightly simple result. Here we can see that this result of 49 gave us that, okay, these two vectors that we have chosen are 12 degrees apart in terms of the angle between them. When we match them both on their tails, this is the angle that they would draw. This is the arc, in quotation marks. So what we can say is that this is very useful property of inner product to give us the idea of how far apart those two vectors are. Okay, so we have talked about inner product, but what about outer product? There is another operation, outer product. And when we, as you can see, when we first made a multiplication by vector transpose and the vector, And now we have vector multiplied by vector transpose. So this gives us an kind of like expanded form of, as a result of this multiplication of two rank 1 tensors, we get a rank 2 tensor. We get a matrix. And so here I have kind of, oh, okay, this is the Discord notification. So what we can, so what we have here is that we get a matrix which every component is a multiplication of single component from each vector and its transpose vector. So also what we can see is that in terms of vector multiplication, this is this really fills in, because what we get is a vector which has a in each of its row has only single element, and we get a single row in the other tensor that we multiply with. Okay, so what does it mean? Well, it gives us certain matrix, and it's let's say its geometrical representation is that we could actually get from one vector we could get the scaled version of the previous one once we input the one vector that we used to obtain the outer product with. So here, for example, we have two vectors that we try to multiply with themselves, multiply against. One is v1. There's v1 and v2. We multiply these two vectors. One will be transposed. The v1 is here in the example, and we get certain matrix. But now, when we try to multiply this matrix by a vector, vector 1, which we previously got as a transpose, which we previously used as a transpose, what we actually get is v2, but only scaled by 38. So this is pretty important result, I would say, and this will come up slightly later in when we describe the quantum states, because this is very very nice to know, and it has a certain connection with the multiplication of the states of the in the quantum hardware. So yeah, so this matrix is an outer product, and when we plug the vector that we used to create it, it gives us the other vector, but scaled. Sometimes down, sometimes up. Here we scaled it up by 38, but we regained it. So that's one thing. Yeah, so these are different types of multiplications that we can do. We have mentioned the inner product, we've mentioned the outer product. So now there is this very, very generic operation as well, which is called a tensor product. The tensor product is kind of like an expanded, it kind of expands one tensor into the other. As you can see here, we in terms of vectors, we bring up the second tensor and we distribute entire tensor into every single component of the first tensor. So here, if we have vectors, we distribute the second vector into every single component of the first vector. Multiply it with this, we multiply then each component of this expansion with the first component of every single of these of this first vector, and then we come up with vector that is incredibly long that expresses multiplication of every single component. This will be very important shortly. Another type of thing that we could do is, for example, a tensor product vector with a matrix, and we also do the same thing. So we distribute this vector, so the second operand, into elements of the first operand, and we get this. So we have obtained a matrix which is way larger. And for example, here we have all the elements from the second operand, which is x1, x1, y1, z1, multiplied consecutively by a11, 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 and so on and so forth. For every single matrix component, we generate way more final matrix components. And here we have a concrete example. So as you can see, we have an identity matrix. Here we have yet another example of now tensor product of one matrix and the other. We have identity matrix and matrix with some components, and we distribute it like this. So we multiply every single component from this matrix in this part of the final result here. And as you can see, the result is that we kind of have to have the matrix components, the second operand, in the left upper corner and the right lower corner, and we get 16 elements. So this is very important. We could tensor product way more elements, and this is the shorter definition that we would use for this operation further on. For example, here I tensor product identity matrix 4 times in a sequence, and what I arrive with is the I tensor 4. This is the notation that also will sometimes be listed. I have seen this in a very similar way written in math papers. And also what we could do is we could represent, and we will do this, represent the array as some sort of, what we would do is we will represent the array as this notation. So this is some sort of like partial notation. We see that there are zeros, but the zeros are pretty special zeros. They are kind of like semi-hollow. This means that this describes a part of the matrix that encodes 16 elements, 4 by 4 matrix of zeros, and this replaces me writing every single zero in this matrix because there are 4 to the power of 4 elements. So that's way too much than is comfortable for me writing. But this shorter notation is very useful for this. So yeah, so we have seen the tensor product. What about the tensor product, or what about when we have something else than real numbers? Because so far we have seen the representation of the real numbers. Well, there is and there isn't. It is problematic and isn't problematic because we have to come up with some new, let's say, new operations for this. So for example, here we have a norm of a vector, and here we have to have some sort of different inner product, because standard definition won't do. It will be very hard for us to square a vector, square the result when there are imaginary components inside of our standard definition of the norm. So what we do here is we make a another expansion to our definition, which is we take not only the vector transpose multiplied by the vector, but we take a vector complex conjugate. What does it mean? Well, it means that we take an opposite, we negate the imaginary component of the imaginary number, because of the complex number, I'm sorry, and what the complex number is the number that has a real component and imaginary component. And imaginary component has the I, which you may know as square root of -1. But to get rid of this, we cannot do it exactly very easily. What we do is we invent new type of transpose, and when we transpose a tensor that has complex elements, we take its transpose with complex conjugate, which means that if this tensor has any elements that are complex, we take a conjugate of this name of these elements, and then we transpose, or vice versa. And what we get as a norm of this vector in complex space suddenly becomes something measurable, suddenly becomes something that we could actually calculate. And this is very, very big. This thing with complex conjugate transpose will be used also in the future lectures. Okay, so that's it in terms of, and we also can do the same complex conjugate transpose on the matrices. We do it pretty much the same as I said with regular transpose. The only difference is that we take the every complex entry, we take a conjugate in addition to the regular transpose. Okay, so now I will be talking about probability. So we could do very quick break, like 5 minutes, and we could end up on this, on the classical probability, because that was always that was also on the agenda for today. Yeah, 1-bit coin flipping and so on. So that was also on the agenda. So let me have a 2 minutes or 3 minutes, and we will go also on that as well. I will probably not make it in time, so we will, because I have spent much time talking about the introduction and the quantum computing landscape. So we will move some part of of today's lecture on tomorrow. I think that's okay. What matters most is that when we go through entire material, and when we arrive at pretty much well understanding of the material, that would be the most, let's say, I would be very happy if if we will arrive at this. So give me 2 minutes. It's already shared. It's already shared. Is the notebook going to be shared on Discord? I mean, this as a PDF I will share, and it is already shared on the Discord. So you can wait a second. Where is it? I think lecture help is yes. So lecture help. Yeah. So this is it. Quantum computing for beginners or all info.
No.
This is
Mateusz,
the
just a question. Can you write on the announcements channel or useful links as well?
oh,
Because you know
that's a good idea.
the category of questions is rather for the participants to ask questions, right? So I think
Ah,
it's just,
okay,
Mhm.
okay.
It
Yes,
can be
yes,
easier.
yes, yes. So I will transfer these after the lecture. I will transfer
Okay, that's
these
fine. No problem.
links into the useful links. So this is a PDF, and you could, yeah, uh, you can go over it at your own pace later on after the lecture. Yeah, so Pavel will help you because I am not the one that send out emails.
Mm-hmm.
The Discord link should have been in the email.
Invitation. It was sent to everyone
Yes,
in the email invitation, but I don't know. Maybe the link doesn't work. I don't know what's going on, so that's why I asked.
yeah, so that's it.
Mm-hmm.
So give me 2 minutes. I will drink some. Oh, so maybe the new link has to be generated.
Yes. So as I said, the link was shared
Okay,
in the invitation email. I'm a bit skeptical about sharing the link to the Discord here on the chat because you know I'm not sure if all the participants registered for the workshop, right? So we send the links only to people who registered, and if you registered, you should have received the link in the invitation email, right? So I will do
so
it, right?
send the email back to Pavel probably that
I
your
will,
link.
I will, I will
Uh,
now share the link. I will share the link. I'm not sure if, I hope that the other links the links that were generated earlier, I hope they will not expire. I hope they will be still active. But yeah, I generated another link here and sent it here.
okay.
So,
So give me 2 minutes. I
okay,
will
thanks.
grab something to drink, and we could go for partially through classical probability, and we will. Um. Oh, the Discord link on the mail still works. Okay.
Good. Thanks.
Okay, so I am back. As I said, 3 minutes. We can talk about probability now. So, about probability, what we will do is very simple thing. Also, this will be a review that will be very simple, I think, for you. So, what we will do is we will focus on the collection of events in one state that could happen and that could evolve the system. In basic way, we say that this collection of events, the total probability has to add to 1, right? There isn't any way for our system to have some probability of 1.2 as a sum of different transitions, let's say, from one state to the other. And what we do is when we sum these A, B, and C events, as you can see here, can entail some real world, let's say, transitions. For example, when we flip a coin, a fair coin, probability of obtaining either heads or tails is equal to 1/2. There is no equal to 1/2. There is no other way that we could say this, that we have anything else. There is, however, a way of explaining other different probabilities in terms of 2 outcomes as something like biased coin, which is that it has a certain preference towards giving us the result of a certain outcome. Let's say heads is being flipped on 80% of the time, and tails only 20%. But always probability of heads and probability of tails always have to equal 1. Well, we cannot really do anything, let's say, anything complicated with this representation. We can get some sort of, for example, ratio of one over another that it explains this bias, but well, it's really nothing complicated. The other way that we could explain probabilities and transitions from one state to the other is through matrix. So when we have a fair coin, we could list our probabilities as a matrix like this. And above, we write states that we start with, and above, right? And on our left side, we write the states that we will land on. So for example, here, if I start with heads, then there is 50% chance that I will land on heads and 50% chance that I will land on tails. This will be important in terms of future, let's say, quantum computing terminology. This will help us understand some of the different events that happen. Here also, when we start with tails, there's 50% chance and 50% chance of landing both on heads and tails, respectively. However, we can express with by listing it like this. We could express more complex cases. For example, we can express that, okay, I have a weather station, and I noticed that when there is sunny, it likes to be sunny for many days. And when it is rainy, it likes to rain more often than it doesn't. So from this from transition from state that is completely different is somewhat harder to accomplish than just being in the same state. This is very difficult to express when you have just a single probability like this, like we have on our left right now. So p heads is 1/2 or p tails is 1/2. This is very hard to express. But for example, here it is actually easier. And what we express is that, okay, so if we have I would say I am not really versed in game theory, but I would say that this when I have thought about this, it's more like let's say state machine that is probabilistic, that it wants to either move from a state with certain probability, it starts with a certain probability and transforms into different state. Does that make clear for you? We could describe it as a bubble. I will do this tomorrow. Yeah, Markov chain. Yes. That would be the better. Yes. That would be better explanation. A Markov chain. Yeah. So for example, we start from rainy, and there is 40% chance that the next day will be sunny. That would be for this example. Or there would be a 60% chance that from a rainy weather we will land on again on a rainy weather. So what we could say is that, okay, we have defined a certain transitions, and this is and in the matrix we express it like this: every single column has to sum up to 1. But the row doesn't need to sum up to 1. This is very important to notice. Sometimes even I get confused at this, and sometimes I just forget about this. But that's pretty much a key idea here, that the columns have to sum up to 1, and the sum of states where x is different state from sunny to x has to equal to 1, depending on regardless of what state we look at. So in these terms, whatever column we look at. Yeah, we have explained, we have showed that these are transition matrices. What about different states? So collection of probabilities that we now have at the moment can be expressed as a vector. Here I actually had to replace this with some sort of a message, with some sort of an image. I will do that after the lecture. What we do is express our state as a column vector, and each state has its own probability. So for example, PA is 0.4, PB is 0.3, PC is 0.2, and so on and so forth. If we do this, we could do a very, very nice thing, which is matrix multiplication to get another vector, to get another set of transitions. For example, here in the first multiplication, we say that, oh, okay, I just copy the first column. That's all right. But on the second attempt of matrix multiplication, I get slightly more interesting result. It turns out that when I do this repeatedly, sometimes I arrive at an equilibrium. And this would mean that, okay, what if, and this has a certain meaning. In this case, it has a meaning of, okay, what if I have done this experiment? What if I have performed infinite number of measurements? What would be the end summary of entire statistic? And this is what we would get. So starting from a sunny weather, we say that this is a transition matrix, right? I have a tomorrow I will use a certain pointer or my interactive board to notice this. I will actually use it now. Epic pen. It runs over. So we multiply this matrix by this state, or rather this state by this matrix on front. We get a transition. Then we do this again and again and again. And at infinity, we say that this is our equilibrium, right? So we have, on average, there will be 57% of our total number of days will be days that express the first part. So, for example, in the previous case, it would be sunny days. It would be sunny days. And in the other example, it would be rainy days. So 42% of entire sample would consist of rainy days. 57.1% would be sunny days. This is what we could arrive at when we have performed infinite number of measurements. So what we do here is pretty much a linear combination by this vector representation of our measurements and total like distribution of these days. What we pretty much say is that we describe it as a column vector by linear combinations of different things. We started with probability sunny of 1. For example, because we started measurements today, we see the clear sky, sun. Okay, that's a 1. But we know we have a transition matrix. So this was our initial conditions. This is V. This was initial conditions. So we can represent this probabilistic state as a sum of different probabilities of different events like this, and these events we can encode as the vector that, as you remember from our first thing, is a certain basis vector. It would be as if every single discrete state, maybe I will have to run this, and every single discrete state can be said of as a distinct event. And as a distinct event, it would be in our solution space orthogonal to all the other states that we try to convey in either this very simple example or our business problem. So let me finish this on here. I will come back to this slide, to this page tomorrow, and we will start doing notebooks tomorrow and some exercises. Because now it is 9 p.m. I will also answer some questions tomorrow if you have after this first day. since this introduction took me quite some time. So, but I thought it would be a very nice addition. So, thank you very much for attending. Let me hear you tomorrow. And yeah, I will hear you tomorrow, and we'll continue on our journey.
Thank you, Mateusz. Thanks for the first session.
Thank you very much.
All right, so everyone, if there are any questions, let's ask your questions on the Discord. Our mentors will be available there. And yeah, let's meet again tomorrow at the same time.
Thank you very much.
Mateusz, I think you can stop recording if you can.